Good afternoon, everybody.
Hello.
All right, just getting everything up here, get the chat up. All right. Let's see. Get the homework. Wait, that's the next section. I need to get 17, 4, and 5 up. All right, let me start today, just like I have been doing, reminding everybody of the schedule. So I don't have the right window up. Yeah, okay, so today we're going to go over homework questions from 17, 4, and 5 because we have our last homework assignment due today. And then we're going to take some questions on surface integrals, actually do some extra examples, hopefully on surface integrals, and then 17.7 Stokes Theorem. That's our plan for today. We have one last class on Monday. So Monday will be the last time where we will meet. We will not meet Tuesday. That'll be like your final exam time, even though it's not due until Wednesday. But Monday we will not be meeting, or sorry, Monday we will be meeting, Tuesday we will not. We're going to release the exam after class on Monday. And I've been thinking a lot about the exam and how different things are now, and how people are working from home, and it's hard not to, I don't know, it's just hard when you're working from home to sit and do the exam with what you have in front of you. So I made an executive decision to change the criteria for the exam a little bit and have it, this can be good and bad, but have it be an open notes exam. So what that means is then you're not stressing about formulas, and you have the notes in front of you. You can look at old examples while they're in front of you, but that means the questions have to change a little bit. So I'm not going to be able to use the same types of questions that I've done before, more of setting things up, explaining things, less like direct computation. Because when you have an old example in front of you, you can just kind of look at it and kind of copy that old example. So we'll still do some of that. There's still some value to that, but expect for the final, expect less computation and more kind of explaining what something is. Because you have so many tools at your disposal now, doing a direct computation on a test is not the same challenge as when you're doing it on paper. So it kind of changes what the testing environment looks like. So one caveat that I would have from that is it is easy as a student, if you know the test is going to be open notes, you're like, well, I'll just look in my notes. I'll have my notes. I'll just be able to flip through and look for something that's similar and kind of figure it out. The problem you're going to have then is, even though you have all this time, you're going to run out of time. Like after 5 hours of flipping through your notes because you don't know where things are because you haven't studied, you're going to like burn out. So you still kind of want to prepare, right? You still want to prepare. You still want to do extra examples. You want to make sure you know where things are. If it were me, I would still do a formula sheet, because I don't want to be flipping through. You've even seen me in class where I'm like, okay, it's in 17.4. Let me go there. I'm going to scroll up. And me, it's just a couple of scroll wheels, and okay, there it's that formula. That, I think that's inefficient. So if it were me, even though I knew I had my notes there, I would still make a good formula sheet. And we talked about, you already have your old formula sheets, so you can have those out. And then for the chapter 7 or section 17.4 and on, I would make a formula sheet for those as well. So yeah, that is the plan. Going to change things up a little bit, but still the same schedule. Final will be posted after class on Monday, and then it'll be due, that's actually due Wednesday, right? Due Wednesday, that's the end of the semester. Oh, and then I need other logistical thing. I forgot to do the extra. We had last exams. Remember we had a couple of like kind of flow, I don't know what to call them, like to the 2 points for like, you technically were incorrect, but it kind of give you a couple of like buffer points there. And I did not have those on this exam. So I'm going to update those and add 2 points to everybody's exam for those kind of buffer points. So you should see that later today. I have it on my to-do list. Oh, and I'm going to make a new folder, actually separate the final folder. And I'm going to put all old exams, I'll put blank copies and links to the YouTube solutions for those. So it'll be a good reference if you want to kind of redo some of those or look at some of those old exams. I'll post blank all the old exams and links to those YouTube videos too. Okay, any course-related questions, logistical questions, schedule questions? All right. It is like surprisingly warm in my office right now. I think it's because I was just outside, and so I got to take the sweatshirt off. So if you have any homework questions, let's focus on 17.4 first. So if anybody wants to type those or just wait till I'm back on here. That's a really good question, Ty, about the exam. Oh, just now. No, we're good. Can you still hear me? Ooh, saying low system resources may affect your audio quality. Try closing some applications. I don't even have that much open. All right. So the way I look at it is the way we were going to do it before was going to be 2 tests, right? We're going to have 2 tests. One was going to be basically units 1 and 2, and then the second test was going to be everything else. So if you think about that, everything else means chapter 16 and 17. So that's half the test was going to be chapter 16 and 17, half the final. And so of that, there's like 8 questions maybe. And so half from 16, half from 17 maybe. So we're talking about like 3 questions probably from the brand new stuff. Chapter 17 is very cumulative. So I can ask you to verify Stokes Theorem for an example. I was going to pull one up today if we have time that says to verify Stokes Theorem. And Stokes Theorem is where you have a line integral, and a line integral is equal to the surface integral under certain conditions. So if I ask you to verify Stokes Theorem by doing both of them, you have to do a line integral of a vector, of a field, and you have to do a surface integral of a field. And so that covers like 3 sections in one question. So there might only be 3 questions, but I think all those topics will be covered. They're so cumulative. So we won't have like 8 questions from chapter 17. That's not, I'm not going to say, oh, it's a take-home exam and you have all this unlimited time so I can write 20 questions. Partly selfishly, because I don't want to grade that much, just being honest. So, so it'll be like a regular exam length, try to make it a regular exam length. And I would guess from chapter 17, like 4 or 5 questions, unless there are some easy conceptual ones, I can like, well, this one should be really short, you know, check if it's conservative, calculate the divergence, super short. So maybe more if you count some short ones like that. But the hard ones are the surface integrals, the line integrals, like all those, not a lot of those. So does that kind of give you some guideline on that, Ty? Cool. All right. Any other questions? Yeah, no problem. You're welcome. Any other questions? Kind of big picture questions, final exam questions while we're talking about it? Ooh, how do we show that points flow inward and outward on a field? How do we show what points? Those are a little challenging. I think I know the ones you're talking about. Do you have, because was there one from the notes that you're thinking of? I feel like there was one from the notes. There's one in the homework, 17.546. Cool, so let's take a look at that one. Some of these are not easy for me, so let me take a look at these. I might use Maple, and maybe I should find a way, you can probably Google and find a good one to plot a field. You can kind of take a look at it. So let's take a look at 46 in 17.5. I remember this one. But I'm not sure if I can do it in the moment. So let's take a look at that one. Find the exact points on the circle at which this field switches from pointing inward to pointing outward and vice versa. What is, it's like getting so small. Okay. All right, so let me take a look. I'm going to take a look at my notes for that one to make sure I use our time efficiently. So if we think about that, I think I want to graph this because I think graphing it is not going to answer the question, but it will help us kind of visualize what's happening when it switches from pointing inward to pointing outward. And I don't know if you are noticing any lag. I feel like I need to restart my computer because I'm hardwired, and this morning too for my class, there was like a lot of lag for me. So just let me know if I'm lagging or if my audio cuts out or anything. So I'm gonna see if I can graph that circle along with the field. So it should be pretty straightforward. I just gotta get Maple started up here. My computer, it's like, man. So first we'll turn on plots, and then we'll do a display because we're going to do two things. We're going to do an implicit plot, x squared plus y squared. It was equals 2, right? And then we'll do x goes from, say, -2 to 2, y goes from -2 to 2. And then we're going to do a field plot. And it was, where did that go? X squared comma y. And again, I think we can do the same thing. Okay. So there's what it looks like. So I can't really make it any bigger. It looks like you can kind of, can you see where it happens here? It looks like it's pointing inward, inward. Let me see if I can like snip this and we can zoom in. I guess I could zoom in on Maple too. I think I can zoom, let's do that. No, there we go. Oh, that is not working. Okay, let's go over here. So kind of looking over here on the left, you see it's pointing inward, definitely inward, inward, definitely outward, definitely outward. So somewhere in here, it changes from inward to outward. On the other side, out, 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 out. Out, 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 out. Oh, here we go. Out, out maybe, and then in definitely. So somewhere here, it's changing as well. So just kind of eyeballing it, what appears to be true at those points where it changes from going inward to going outward?
When it kind of looks like at like pi over 4 or something, like, you know, like pi over 4, 3 pi over 4.
Okay, I see what you're saying, like on the unit circle.
Yeah.
Okay. That doesn't help me though. That's just a guess for where it is. So my question was, what appears to be true there? Because that's a good guess for where it appears to be if we're going on the unit circle. All right, but that's not going to help me find it.
It looks like it's going from inward to outward at those points.
Oh, I
So
know.
like, yeah, so like before, that's just what I'm thinking.
Yeah, Max, were you going to say add something? Oh, you have no audio again, man. your Bluetooth disconnected or something, or make sure your cord is all the way in. I've done that before too, where it's not like totally clicked in. Yeah, still nothing. Daniel's guessing the flux is 0 at that point. I hadn't thought about that. Max is typing, so we'll let Max type. Yeah, it does definitely look symmetrical, right? The same above and below. So what I'm noticing is if you look at the vector here, if you look at these vectors, right at this point, what appears to be true, if we had to interpolate, what appears to be true about the vector that's right at that point?
It's tangent to the curve.
Tangent to the curve. So I think that's the fact. Now, Daniel might be right, might be able to do it that way too. But the way that I did it was I said, okay, at these points, the field is parallel or tangent to the curve. So we have our field again. It is x squared comma y. We have our curve is x squared plus y squared plus or equals 2. So one thing we could do is we could say, we could parameterize the curve. We could do the unit circle if you want, but the radius is square root of 2, so we have to scale it. Square root of 2 cosine t, square root of 2 sine t. Okay, on the particular path, my field will be x up from the path squared. So that's 2 cosine squared t, and then square root of 2 sine t. So what I have is I have vectors that are kind of in the direction of the, they're not in the direction of the curve. They are from the origin like out to the point. And then we have these field vectors are the vectors kind of at that point. So how do we find those points? How do we find those points if we're saying that the field vectors are parallel to the curve at that point? Any ideas? So here's what I was thinking is if you look at that point again and just focus on, here's my r vector, whatever that point is, at whatever that point is, and then my tangent vector is here. And we know for this particular curve, those r vectors are always going to be orthogonal, they're always perpendicular to the tangent vector on a circle. This isn't always true, but if r is constant, if the magnitude of r is constant, then they're always going to be orthogonal to that tangent vector. So what I could do is I could say, well, I want this to be parallel to the tangent vector. So one way to do it was just say, well, that means I want that field vector to be orthogonal to the r vector, because the r vector in this case is always orthogonal to its tangent vector as well. Okay. I don't know if this logic is clear, but we have a point here where we want the field, we want that vector from the field to be orthogonal to our position vector. So we want those to be orthogonal. How do we know if two vectors are orthogonal?
Dot product equal to 0.
And so let's see where that leads us. And unfortunately here, I think we're going to have a really hard time solving this one by hand. We could use some trig identities maybe. It's clear here if you look at this now. I think at least as Calc 3 students, we can all recognize that this is an equation, and it's equation in a single variable t. So that should tell us where on the curve, what t values on the curve do we have this situation where the field is orthogonal to the position vector. I don't know how much work we want to do. I was thinking we could do cosine t times and then take one of the cosine squareds and do 1 minus cosine squared. And I'm not sure that's going to lead us anywhere. Or 1 minus sine squared. I don't want to waste too much of our time solving this algebraically. I think for this particular example, using some technology would be reasonable. So let's see if we can. Ooh, I don't know if I know Maple can solve equations, but I don't know if I know how. Like look up the help file. Solve, give an equation, tell it the variable. Okay, well, let's give it a go. Solve, and what do we have? 2 times the square root of 2 times cosine of t cubed minus, was it minus? Nope, plus 2 times sine squared equals 0. Solve that for t. Oh, bunch of answers. Ooh, we did something wrong here because
It's supposed to be plus 2 sine squared t.
plus, I was going to say, do you see how, because we know the answers, we know where they're supposed to be, and I got pi over 4 and negative pi over 4, so I'm like, well, that can't be right. Yeah, I even checked the sign, right? So there we go, 3 pi over 4, negative 3 pi over 4, plus some other weird stuff. Like, well, I don't even know, what is this I thing? I don't even know what these are. So there's some other more abstract answers there to this particular equation, but here's the two, and like you nailed them, you knew where they were, but it isn't enough to say, well, looks like they're 3 pi over 4 and 5 pi over 4. We kind of want to get definitively here, but this was a hard one to solve that resulting equation, to try to get that just by hand. Yeah, Ryan's wondering, is there a different method to solve this that wouldn't require technology? I'm trying to look at, I did it kind of the way I was looking at the way the textbook did it, and they did it a little bit differently from this. And I'm not sure, I think like this way makes more sense to my head, but it results in an equation that's challenging to solve. So the way that they did it, and I think you can actually end up solving this one the other one. So if you do the tangent vector for the field would be 2x and 1, the tangent vector for the field. And on our path r, that would be 2, what is x? Square root of 2 cosine t, comma 1. And the tangent vector for r would be, that's r prime, that would be negative square root of 2 sine t and square root of 2 cosine t. And we want the tangent vector for, yeah, you're right, Ryan, right? Right, it would be really harder, yeah, if the shape was more complex. Yeah, because the shape was simple, we were able to say, oh, because it's a circle, the field will be orthogonal to the radius. Yep. So this method, I think, is a little more flexible, but to me, it's just a more abstract. Maybe that's just me. So the tangent vector for the field would be 2x comma y. So the derivative of the field, the derivative of my position vector, and they're parallel. Let's see, the curve parallel to C when the tangent vector for the field is some multiple of the tangent vector for the curve. So we need 2 square root of 2 cosine t comma 1 to equal some constant times negative square root of 2 sine t square root of 2 cosine t. And I'm not sure if this is going to help us at all, because now we need to solve the system 2 square root of 2 cosine t equals c, actually negative c square root of 2 sine t, and then 1 equals c times square root of 2 sine t. So this is the other method we could use where we don't need to make that assumption that the field is normal to the R. I feel like we can just solve for C in the second one. Maybe this isn't that bad. Square root of 2 sine t. And the first one becomes 2 square root of 2 cosine t equals negative 1 over square root of 2 sine t times square root of 2 sine t. Well, this is promising. So 2 square root of 2 cosine t equals negative 1. I feel like this doesn't seem quite right. I was hoping this would be negative 1 over square root of 2. Why is it 2? Because if it was negative 1 over square root of 2, that would be the negative, that would be 3 pi over 4 and 5 pi over 4. So we have an extra 2 in there for some reason. Yeah, when I was solving this before, I got stuck here too. When I was solving this on my own, and so I used that other fact. So I don't know, Ryan. I think we're close. Like, it feels like this should work. Why doesn't, but somewhere in here, something got lost. Before we move on to the next one, I want to just do one more attempt here and just let's take a look and see what the solutions have for this one. Point, was it 5, number 46? Okay, well, they use kind of similar reasoning. Whoa. You see that? So the field switches to an inward pointing to outward pointing at points where the tangent to the circle, where it is tangent to the circle. Okay, that was good. Like we knew that. Okay, it should be orthogonal to the normal of the circle. The normal to the circle is a multiple of xy. So we want to find when on xy so that the dot product of those two is 0. with x squared plus y squared equals 2. So their fact is this key fact, the normal to the circle is a multiple of xy. So they want to find xy so that the dot product will be 0 on the circle. And that leads to that equation that they have there. And the solutions are x equals -1 and y equals plus or minus 1. You want to take a screenshot of that? For future reference, see if you can digest that. That's a challenging one for me. Okay, we made a good and valid attempt at that one. What other questions do we have from the homework? 17, 4, or 5? Anybody else? Have any other homework questions? All right, I'm not seeing anything else here. So if there are no additional homework questions, let's do some more examples from 17.6. We had this extra practice where we did some practice parameterizing surfaces, but we haven't done any surface integrals. So let's try to do our best to try to do a couple of those. These are especially where good notes will help, because there are references where you can reference back, oh, this is the same shape surface that this other example was, so I can use the same parameterization as this other surface. So I think that'll come into play here. So we were looking at, this is a 17.6 extra practice. If you don't have it yet, you can get it under Unit 5. There should be a 17.6 extra examples here. All right, so let's take a look here. We are trying to find the area of the following surfaces. So first of all, the key here is a surface integral is some f of x, y, z dot ds, or sometimes it's written surface integral f of x. I think your text writes it dot product with n ds. And so the key is, if the function is 1, then you just get the area. So that's what we want to do here, is we want to do the surface integral of 1 dot ds. And let's go in our notes. 17.6 surface integral. It's on like the 4th page. There it is. So it's this guy right here. This guy right here. Let's see if we can, I don't want to do a snip. Let me see if I can copy it this way. Kind of. Okay. So we need to parameterize our surface, and then we need to find some tangent vectors, find their cross product, find the magnitude of that. Okay, parameterizing the surface. This is a hemisphere, and so this is where previous examples is super helpful. The sphere, and I think this was from example 5. I keep referring back to that one. Example 5 is a sphere, and it does all this stuff. So here's a sphere. Temperature on a sphere of radius a. Okay, and so here we have all this stuff already actually, but we'll kind of write down what we need. So it's basically spherical coordinates. A sine u cosine v, a sine u sine v, a cosine u. And so our a is, our radius is 10. So 10 sine u sine v. Need more space. Wait, hold on. I feel like I mixed that one up. Sine u cosine v, that's this second one. So this is cosine v, 10 sine u sine v, and then 10 cosine u. Double check there. So I'm looking at a sine u cosine v, a sine u sine v, a cosine u. Okay, and then from example 5, we already have the magnitude of the cross product of those two tangent vectors. If you want to watch the video, we did a pretty full derivation of that. It's a lengthy derivation, but there's some trig identities that you can use there. That's all in the video. But the nice thing is you end up with just a squared sine u after all that. So you find a tangent vector in the u direction, you find a tangent vector in the v direction, you find the cross product, and then you find the magnitude of that. It's a lot of work, and you end up with a squared sine u. So that'll be 10 squared, it'll be 100 sine u. So our surface integral then becomes the double integral over, let's see, we still have a little bit of work here, but we have 100 sine u, and then du dv, but of course we need bounds. We need bounds. The full sphere, for the full sphere, u is phi, so from 0 to pi, and then v is theta, 0 to 2 pi. But we do not have the full sphere. We just have the hemisphere, z greater than or equal to 0. So we have to modify that. Maybe we won't go all the way around for theta. Maybe we won't go all the way from 0 to pi for phi. Anybody have any thoughts about if we only want the top half of the hemisphere, how that's going to change our bounds?
For you, would it just be 0 to pi halves?
Yeah, I think that would do it, because that would be just the top, right? 0 and then just to pi halves and then stop there. And don't keep sweeping all the way to the bottom. Yep. So 0 to pi halves, and then v would still be 0 to 2 pi. So you see how a lot of these, it's like there's almost more work just setting this whole thing up and figuring out what is the surface, what do I integrate, what are the bounds. That's a lot of work, and that's something that, like, it's not unreasonable to ask you to do that with references in front of you. That seems like a reasonable thing to do. So that's why I think, you know what, let's just change the criteria for the final and let you have some notes in front of you. All right, this is a pretty easy integral, relatively speaking here. let's see, we have 100, and integral of sine is negative cosine u from 0 to pi over 2. Negative cosine of pi over 2 minus negative cosine of 0. That's too many negatives. I should have just factored it out. Cosine of pi over 2 is 0. And cosine of 0 is 1, so we just get 100. So that'll just be 100v from 0 to 2 pi, so 200 pi. Huh. Just a quick check for yourself. Does anyone know the surface area of a sphere? You could Google it if you needed to. It's 4 pi r squared. And so we have a hemisphere. 2 pi r squared would be ours, and the radius for our hemisphere is 10, so 2 pi times 100. So, not saying that a surface integral is an efficient way to find the surface area of a sphere, not at all. In fact, very inefficient. But if the surface was more interesting, then this would be a way you can get the surface area of some really irregular function. This one just happens to be a sphere, and so it's a formula you already know, but it doesn't. The problem is the ones that are more complex give you like impossible integrals to do. So you kind of, we're just dabbling in it here. So we're trying, most of the integrals end up being, most of the surfaces end up being very repetitive. So we keep doing the same surfaces because they're simpler surfaces, cylinders, spheres, things like that. All right, any questions on this, this example here, number 22? All right, one last one from 17.6. This one is, we actually have a function that we're going to do, or a field, excuse me. We're going to find the surface integral of a vector field across the surface. And here's our surface. Z is equal to cosine of y. This one, it says the directions where you could use either explicit or parametric descriptions, but you'll notice that our surface Z here, which is cosine of y, it is just a function of x and y. So we do not need to parametrically define it. We don't need any u's and v's. There's a different formula if your surface is a function, an explicit function of x and y. So we go back over to 17.6. We have this guy right here for the surface integral. Oh, sorry. There's something running in the background here on my computer, I swear, because it is behaving very slowly right now. So it's going to be important for you to recognize, do I have a function of x and y, and I can use this explicit one? Or do I need to first define my surface parametrically? Oh, sorry. Shoot. That was the function. We need to get the one where it's a vector field. It's similar. It's way at the end. It's right here. Oh no, what's happening? Oh, my whole computer is like Driving me crazy right now. I've been using the description that I'm like limping to the finish line. I don't know if anyone else feels that way, but like I'm feeling it. Definitely feeling like I'm limping to the finish line this semester. Okay. Now we have the right one. We have the surface integral of a vector field when the surface is defined explicitly. And that's what we have right here. Okay, so let's see here. Looks like we need the partial derivative of z with respect to x. That's convenient, that's 0. We need the partial derivative of z with respect to y. That's negative sine y. So we're going to do the double integral over our field e to the negative y 2z xy dot product with the opposite of the partial derivative with respect to x, so that's still 0. The opposite of the partial derivative with respect to y, that's sine y, and then 1. Okay. And then dA, we can do dy, dx. It doesn't really matter either order because you will see here we have a rectangle. The absolute value of y is less than or equal to pi. So that means y goes from negative pi to pi, and then x goes from 0 to 4. If you're paying attention here, there's a little bit of an issue with this. It's subtle, but you'll see it here. When I take the dot product, e to the negative y times 0, that's just 0. And then I get 2z sine y plus xy times 1, dy dx. So what do you notice there? Did anybody see it already?
There's a z.
That's not good, right? This is a double integral in y and x. We have a z. So how do we handle that?
Well, the z just equals cosine y, doesn't it?
Exactly, yeah. So we're doing a surface integral. Yep, you're exactly right, Max. So on this surface, z is equal to cosine y. So it's kind of like the ones where we had the path and we kind of substituted those into the field because we said, well, on the path, here's what the field would look like. So on the surface, here's what the field will look like. Instead of z, it'll be a cosine y there. So now I do have a double integral that's doable here. 2 cosine y sine y plus xy dy dx. So from there, it's a pretty straightforward double integral. So I kind of want to pause and see what questions you might have from setting this up. So anybody have any questions so far? All right, not seeing any. Let's integrate y then, 0 to 4. Well, the second one will be easy, xy squared over 2. And then for the 2 cosine y sine y, you can say, well, u is sine y, so du is cosine y dy. So what you're going to end up with is, well, you have 2 u du, so the integral will just be u squared. So that's going to be sine squared y. And that's all still dx. And this is very convenient here. You have sine squared of pi, that's 0, plus x times pi squared over 2, minus Wait, what? Sine squared of negative pi plus x times negative pi squared over 2 dx. Sine squared of negative pi also 0. But then don't we lose all the x's too? Just get 0. I haven't done this one yet. Huh? Oh, pull this over here, you can see we do get 0. 46, you get 0. There's our integral, same integral we just had. So yeah, crazy. So for that one, there is no flux across the surface. There is no flux across that surface. So no net flux across the surface. Some of them must be coming in, some of them going out. And so when you sum up over the entire surface, no net flux on that one. Interesting. All right, any questions on that one, on finishing that one up? Okay, so I just posted earlier today the 17.7 Stokes Theorem video. We can quickly summarize it. It's actually a relatively simple idea, and then I just did a bunch of examples of it. So Stokes Theorem is basically the three-dimensional version of Green's theorem. So Green's theorem says, hey, if you want to find the circulation around the outside, this is in 2D, you want to find the circulation around the outside, you can double integrate the curl instead. And those would be equivalent. Line integral, curl. So Stokes theorem is the three-dimensional version of that. If you have some surface whose boundary is a curve, you can find the line integral of the boundary, or you can find the surface integral, and they will be equal. Line integral, surface integral, they're equal. So Stokes theorem is basically the three-dimensional version of Green's theorem. You can find the line integral, and that should be equal to the double integral of the curl over this surface, and that's what Stokes theorem is. So the example, I don't know how much we'll be able to do here. Let me copy this. We'll see. Maybe let's start with setting up the integrals. How about that? It's basically like that one we did where we wanted to verify Green's theorem. The example that I have here, I just want us to verify Stokes theorem. So let's start. Let's see. It's 2:54. We've got 10 minutes left. That's doable. Maybe. I haven't done this one. These I only assigned 2 problems from this. If we were in a normal semester, you're not going to have to turn any in for this. So try to have it your goal to do a couple of these if you can. Even if you can only do one, where you do the line integral and you do the surface integral, and you can do them enough where you get those to be equal. Then you're like, okay, I have it right because they're equal. That I think should be your goal. If you can do one good one, that's kind of what the point where I want you to get to. So let's see here. The field is 2z, negative 4x, 3y. S is the cap of the sphere. So the sphere is radius 13 above the plane z equals 12. So if you think about that, all that's going to be is just a little cap of the hemisphere. Like, not a hemisphere. It's just a little cap of the sphere up here at z equals 12. So the radius is 13. So it's only one more unit up. It's just a little cap. I think the line integral is going to be way easier here. So the idea is you have this curve, which is going to be a circle, and then you have the surface that's too steep. The surface S. So C, the path is a circle, and then the surface that's above it is, it's not a hemisphere, it's the cap of a sphere. So we have two integrals. We're going to have the line integral around the circle, and then we're going to have the surface integral over the cap. There is one caveat. Remember for Green's theorem, there was a specific orientation. Do you remember what the orientation was, where the curve had to be?
Counterclockwise.
Right, Michael, it had to be counterclockwise. There's something similar here. But what it is you're assuming here, it's saying C has counterclockwise orientation and S has a consistent orientation. Whatever the orientation of the surface is, it has to be consistent with the path. And the way we do that is, if you think of the orientation outward on this surface, it's this right-hand rule. Think of the cross product. It's kind of like that. So if you follow the path with your right hand, your thumb should point in the same kind of orientation as the surface, like usually outward. So your right-hand rule, the thumb should point in the direction. If you watch the 17.7 video, you'll see that's relevant on a couple of them. That actually, you kind of have to do opposite orientation of what you might want to. So for ours, our orientation on the curve is going to be that way. So let me look at the curve. Looking at it from above, it's really like a level curve. C is a level curve of the sphere. What do I mean by that?
That it's like, it's kind of like a part of the sphere almost. Like it represents some sort of aspect. I don't really know how to say it, but it's like.
Mm-hmm. Yeah, I think you're getting there. Like it definitely is part of the sphere. So let's think back to level curves. There's a specific meaning for a level curve. Max is typing here. So Max is saying like a level curve is a specific z. There's a very specific z. So in this case, we would say x squared plus y squared plus 12 squared equals 169, which means x squared plus y squared equals 25. And so at that specific level, it's a circle radius 5. You're exactly right, Max. So that's our curve C is a circle radius 5. Now it's at a z value of 12. Keep in mind, this is at z equals 12. So if we're gonna do a path for our curve C, it has to be a 3-dimensional path, and the z value is 12. I drew it kind of in the xy plane, but it of course is elevated up 12. And then orientation, let's see, we were going from positive x to positive y. Let me draw it in red here. We need to get that right orientation. So that's the orientation we're using. That's the orientation. So positive x to positive y, that's this way. Okay. So I think we should just be able to use the unit circle because that's the orientation it goes in. And just scale it by 5. So 5 cosine t 5 sine t, and then 12. How are we doing with that? All right. I think if we can set up these two integrals, that will be a major accomplishment. All right, we want to do the line integral of the curve, the field dot dr. So this, hopefully you've been doing enough line integrals where this will be easy for you. If it's not, it's okay. You've been learning a lot of stuff here. But we should be able to, let's see, my field is 2 line integrals by now should be manageable. They were a little wild when we first did them, but they should be manageable by now. So I'm just copying my field down here, 2z, negative 4x, 3y. So 2 and then z was 12. Negative 4x was 5 cosine t. And then 3y, 3 times 5 sine t. And then dot product with dr, which will be r prime of t. Negative 5 sine of t. There's our r's up above here. 5 cosine t, and then 0 dt. We're missing bounds, but we can fill those in later. So 2 times 12 times negative 5 is negative 120 sine t. Minus 100 cosine squared t. Oh, and then plus 0. Nice. dt. Then we need some bounds. You probably know what they are already. I should have done that when I did the path. So I should have specified up here what the bounds were. But we need to go all the way around the circle. So it's 0 to 2 pi. So that'll be the bounds of our integral as well. All right, how are we doing on that? Okay, so we're not going to do that. We're just going to set that up so that, and that's an easy enough integral to do. Take you a few minutes. But let's see if we can set up the surface integral. Let's see, it is the curl of f. Ooh, this might not be possible. Dot ds. Yeah, I don't know if we have enough time for that. So that's the double integral over the surface of the curl of f, the dot product with tu cross tv dA. So the problem with this is we're going to have to parameterize the surface. So we need to parameterize the cap of the sphere. Then find tu cross tv again. And we also need to find the curl of the field. Now, this is not an impossible problem. If we had even 5 more minutes, we could set this up, because the first part of this is actually doable in a short amount of time. It's the cap of a sphere. how are we going to get the parameterization of that and the TU cross TV? Give you a hint. Notes, section 17.6, example 5 again. That was it was a sphere. This was a full sphere. But then here's your TU cross TV. It's right here. That's ugly. It's ugly, but there it is. There's your radius. A squared is your radius. The one thing that we would have to do is that was a whole sphere, and we just have a cap. So somehow we'd have to figure out if this is 12 and this is 13, we'd have to figure out what the maximum phi is. Right? It doesn't go from 0 to pi over 2 or 0 to pi. We have to do like an inverse sine or something, or inverse cosine, something like that. And then the curl of f, let me finish with that because I know we're running late, always these days. The curl of f is the one that's a little more work. That's I, j, k. And then these operators, partial derivative with respect to x, partial derivative with respect to y, and partial derivative with respect to z. And then it's the field, 2z, negative 4x, 3y. And so you just find that cross product there. So it's totally doable. And I think if this was an exam question, what I would ask is I would ask for a simplified line integral, which we have, we're done, and a simplified surface integral, which we are not done. Because we need to find, we have the ds, because we have the TU cross TV. We have that. That's done. That's from example 5. We don't have the bounds though, so we have to think more about the bounds. Theta goes from 0 to 2 pi, so v goes from 0 to 2 pi, but it's the u. It's the u that just goes a little bit. We'd have to figure that out. And then we don't have the curl of f, whatever that is. So we're like 2/3 of the way there. And so I think for a problem like this, if I'm going to ask this, is I'm just going to ask you to set up and simplify the two integrals. And so when you're done, you shouldn't have any vectors in there. You should have an integral in terms of t, and then an integral in terms of u and v. You should have a single integral in terms of t for the line integral, and you should have a double integral in terms of u and v for the surface integral. Okay, it's already 3:09. Kept you late again today. I feel like I've done that every day. We always get stuck in the middle of these problems, and it's like, I don't know. So for tonight, you have 17.4 and 17.5 homework. We've done a few of them already. So I know we did 46 today. I feel like we did a couple other ones. So hopefully you were able to get those done. No Dropbox yet, huh? I'll get that Dropbox up. So that's due by the end of the day today. And then it's time to start getting ready for that final. So we have one more video for me to make and for you to watch, 17.8. And then we will meet again for the last time on Monday. Monday will be our last time. We'll try to do one 17.8 example, kind of like today we did one 17.7 example. We'll try to do one 17.8 example and then release the final exam after that. And you can wait until Wednesday to do it if you want, and try to do some extra studying. That is totally fine. My goal is to plan for the exam to be like 2 class periods worth. So I'd like it to be between 2.5 hours worth. That's my goal, is for it to take about that, because I know you have other stuff and I don't want to just say, well, now you're at home so I can write this really long final. So I want it to be about 2.5 hours. I know some people are really using the extra time and taking advantage of that to double check your answers and all that, and that's fine. That's cool. So if you want to do that, you may want to start a little bit earlier. Okay, I think that's it. Any last questions before we log off for today? All right. Well, enjoy the rest of your day. It's still pretty nice out. I have an hour-and-a-half meeting starting at 3:30 today. Okay, I'll see you.
Yeah.
All right, everybody. Take care. I'll see you Monday.